Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. We are in module 10 discussing about X-ray diffraction, and this is lecture 5, and will continue with the discussion about intensity of diffracted beam. So, we have until up to now we have seen that how an X-ray beam interacts with an electron in an atom and how it produces the coherent scattering in form of by Thomson's effect, and then a modified incoherent scattering in form of Crompton scattering. So, these are the two types of X-ray scattering that can happen from an individual electron within an atom. And then in the last class we were discussing about how these electrons, how these scattered beams from the electrons can be added up, so that we can finally get an expression for the intensity, scattered X-ray beam intensity for an entire atom. So, that's what we were discussing, and there we finally derive this atomic scattering factor, which basically expresses the relationship between the wave scattered from individual electron with the final wave that is coming out of an atom, which is a summation of all these waves scattered by individual electrons, and that we have derived. We have seen that this depends, the atomic scattering factor depends on the direction at which this scattered beam we are adding them up. So, it depends on the phase relationship between the electrons, the waves coming out of individual electron, it depends on the phase relationship between them, and depending on that, in finally the direction of the scattered beam, we get an expression for this calculating the entire intensity or amplitude. We calculate in terms of amplitude, and then amplitude we can simply get the final intensity from this amplitude itself. So, there we will continue that discussion today, a little bit of atomic scattering factor, and then we will try to derive a relationship between diffraction and scattering, what so special about diffraction, and finally we will then start with our discussion about scattering from an entire unit cell. Sorry, this should be scattering from an entire unit cell. Okay. So, atomic scattering factor, the first thing, again we discussed the same thing earlier also, that atomic scattering factor F depends on the two things, sin theta, that is the angle between X-ray incident X-ray and the scattered X-ray beam. So, it depends on that angle. So, as the angle increases, the atomic scattering factor decreases, that is one thing. And second thing, it also depends on the lambda value, that wavelength of the incident X-ray. As the wavelength goes down, then the F also is decreases. So, these two values together, these two terms together, sin theta by lambda, this dictates the atomic scattering factor, and atomic scattering factor is highest in the forward direction, where sin theta is basically 0, and then again it decreases afterwards continuously as the sin theta is increases, and lambda also together it decreases continuously, and in the backward direction, where again the theta equals 90 degree, there also the atomic scattering factor is very low, and it can be also very low for very short wavelength. So, this is the kind of relationship that atomic scattering factor shows with sin theta and lambda. This we saw in the last class. Okay. Now, the point is, we have also discussed about this, the scattering factor is only applicable to the coherent part of it, the coherent scattering, coherently scattered beam, that means the Thomson scattering, which is only able to take part in the diffraction. We have discussed this many a times. Crompton scattering, inherent or Crompton modified scattering cannot take part in the diffraction process, because the intensity of this unmodified intensity of this Crompton scattering beam is very much random. So, it has a very random relationship, it is kind of an incoherent scattering, and in that process the beam that is generated out of Crompton scattering process, that beam does not have a definite phase relationship with the incident X-ray beam. But of course, the way the Crompton scattering generates, from there we can try to bring a relationship between the Crompton scattering, the atoms, or the finally the the intensity of the Crompton, intensity of the wave, X-ray wave coming out of the Crompton scattering due to the Crompton scattering between incident X-ray and the electrons. So, we can try to find out an expression for that also, because as you remember, I said the Crompton scattering is important because it forms the background in the diffraction process. So, finally basically what happens when you capture the intensity in a detector, in an X-ray detector, you capture the intensity that will capture not only the diffracted beam, it will also capture the beam coming out of the Crompton scattering, which will form the background. So, it is important to know exactly how much Crompton scattering you are going to get out of this individual atoms. Okay. So, this intensity of the Crompton scattering for an individual atom, from one single atom, the intensity of this modified Crompton scattering that is coming out of an atom, this will be related to the number of outer shell electrons or number of loosely bound electrons which are present in individual atom. That means, because that is how the Crompton scattering is generated. Basically, in Crompton scattering what happens, the incident X-ray beam comes and a loosely bound electron, that is usually the outer shell electrons or valence electrons, those electrons it can hit, and that electron then gets some momentum, some kinetic energy, and that just goes out of the atom. So, in the entire process, basically it's a interaction between the incident X-ray and the loosely bound electrons. So, if the number of loosely bound electron or the proportion of loosely bound electron within an atom, if that increases, then the intensity of the Crompton scattering, intensity of the modified radiation, Crompton modified radiation, that also will increase. So, that means the relationship between the atomic number and the Crompton modified scattering is that there is not an exact relationship that exists, or that relationship is a very difficult one. We are not going into this, but basically the intensity of the Crompton scattering will increase as the atomic number decreases, because if the atomic number decreases, what happens is that higher the atomic number, then higher will be the number of electrons in the outer shell as well. The positively charged nucleus will not be able to bind those outer shell electrons with a strong force. If it is light element, low atomic number element, then electrons are far more closer to the positively charged nucleus, and then this energy with which, or the binding force with which the positively charged nucleus is attracting this outer shell or this electrons will be much higher. So, Crompton scattering, basically as the number of atomic number increases, outer shell the number of electrons that increases, as we are if the atomic number is increases, then the number of I am possibly telling in the other way around. If the atomic number increases, the Crompton modified, the intensity of the Crompton modified radiation, that increases as the atomic number decreases, because if the atomic number decreases, there will be more number of loosely bound electrons will be present there. When we go for a higher atomic number element, then the positively charged nucleus will have more energy, much more positive charge will be there in the nucleus, and then that will be able to bind all the electrons with a much stronger force. If the atomic number decreases, then there will be less charge in the nucleus, and this small amount of charge will not be enough to bind all the electrons which are present in the outer shell. So, those loosely bound electrons number of loosely bound electrons, proportion of loosely bound electron, I should not say exactly the number of loosely bound electron, the relative proportion of loosely bound electrons will increase as the atomic number decreases. That means the intensity of the Crompton modified, the relative intensity of the Crompton modified material or Crompton modified scattering will also increases as the atomic number decreases. Basically, one thing you must understand here, the inner shell electrons which are tightly bound. So, inner shell electrons are responsible for Thomson scattering, because if the inner shell electrons are hit by the incident X-ray photon, they will be, since they are tightly bound by the nucleus, they will not be able to go out of this atom. They will be there and they will be oscillating about their mean position. But if the incident X-ray beam is hitting an outer shell electron that will have less amount of, or that will be loosely bound with this nucleus, because this is in the outer shell. So, those electrons will be able to produce a Crompton radiation or Crompton modified radiation scattering, X-ray scattering. So, that is the relationship. So, basically if the atomic number decreases, this proportion, relative proportion of inner shell electron and outer shell electron, this will increase. So, proportion of outer shell electrons will increase if the atomic number decreases. So, the intensity, relative intensity between the Thomson scattered X-ray beam and Crompton scattered X-ray beam, this will change. So, this relatively compared to the Thomson scattered coherent scattering, incoherent scattering, Crompton modified X-ray intensity, that will increase for lighter elements with lower atomic number. And this is why for low atomic number materials like for example carbon, oxygen, hydrogen, for low atomic number elements, it is producing more amount of Crompton scattering rather than producing coherent Thomson scattering. That is why diffraction, getting a diffraction pattern from this low atomic number elements like carbon, oxygen, nitrogen, basically for organic materials. If you consider the organic materials containing mostly carbon, oxygen and hydrogen. So, for this materials, the Crompton scattering will be much more prominent than the Thomson scattering, and that is why compared to the diffraction peaks, the intensity, the background intensity will be too high. Okay. So, that is one of the, and that is what is one of the major problem of capturing a good diffraction pattern for a organic material or low atomic, consisting of low atomic element, low atomic number elements. So, that is why for organic materials X-ray diffraction, for polymeric materials, for organic materials X-ray diffraction is not the good process to identify their structure. For them you have to take special care and in order to reduce this background, in order to reduce this Crompton scattering phenomena. Anyway, so this intensity of the Crompton scattering also increases with sin theta by lambda quantity. So, this is exactly in the other way around as the Thomson scattering. For Thomson scattering we have seen, Thomson scattering means basically atomic scattering number. So, atomic scattering number decreases as sin theta by lambda increases. So, that is the relationship between sin theta by lambda and atomic scattering factor when we consider only Thomson scattering. But when we consider something like Crompton scattering, the Crompton scattering has a direct relationship with sin theta by lambda. As sin theta by lambda increases, Crompton scattering also increases. How it is happening, we are not going into that. Basically, if the wavelength of, basically it means if the wavelength of the electrons is decreasing, that means the electrons are now coming with a higher energy, a shorter wavelength, that can able to, that higher energy with, for the shorter wavelength it will have a higher energy. So, after it will be able to transfer more amount of kinetic energy, and the scattered beams now will have much, the intensity of the scattered beam will be much more. Basically, that is what. So, if the wavelength of the incident electron decreases, if we use a shorter wavelength, the intensity of the Crompton scattering will also increases. That is the relationship. That is why sin theta by lambda, this relationship, if sin theta by lambda increases, the Crompton scattering also increases. And if we now see that this atomic scattering factor for, if we compare two elements, higher atomic number elements like iron versus lower atomic number elements like hydrogen, carbon or oxygen, if we see them, then we will see that this, for the higher atomic number elements, the atomic scattering factor, finally the intensity, atomic scattering factor is simply the amplitude of the waves coming out, or amplitude of the wave coming out of the entire atom divided by the amplitude of the wave for a single electron. Does not matter whether it is Crompton scattering or Thomson scattering. If we take it, then we will see that atomic scattering factor varies very strongly with sin theta by lambda in case of higher atomic number element, where only Thomson scattering is mostly contributing to atomic scattering factor. Whereas, if we look at this lower atomic number elements like carbon, oxygen, hydrogen, we will see that atomic scattering factor is not that much of a strong factor, or strongly depends on sin theta by lambda. Because what happens is, the Thomson scattering factor, if we only consider the Thomson scattering, then that will decrease the atomic scattering factor, that part will decrease with sin theta by lambda, but the Crompton scattering will increase with sin theta by lambda, and together these two will go into other two different directions, and altogether then the atomic scattering factor, the decrease in the overall intensity of the scattered beam from one single atom will be not that sharp. It will not decrease that sharply will sin theta. These two affect Thomson's and Crompton scattering, the way they varies with sin theta by lambda. This will be possibly some way mitigate each other, or some way they will be balancing each other. So, that is the importance of considering the Crompton scattering as well in addition to Thomson scattering in the atomic scattering factor. So, the point is atomic scattering factor does not know whether it is a Thomson scattering or Crompton scattering. All it knows is that expression, that is the power of that expression. It only knows the amplitude of the wave or intensity of the wave coming out from an entire atom divided by the intensity of the wave coming out from one single electron. That is what. So, that is how we can explain for at least for lighter elements where the variation is not as strong as the higher atomic number elements. In order to explain this kind of variation, we have to also consider the Crompton scattering. That is the point. Anyway, now if we look at the diffraction and scattering, the entire phenomena, and that entire X-ray electron interaction, this entire phenomena is shown in this chart. This will help us to understand what basically is the diffraction. So, when an X-ray incident, X-ray beam incident on a material, some part of this X-ray beam will definitely be absorbed by the material. The rest of the X-ray beam which is coming out of this specimen, this will be 95% of it will be transferred to heat, first of all. Then we will have a transmitted beam as well, no diffraction, only in the forward direction we will have a transmitted, no scattering, nothing, forward scattering. If we take forward scattering, okay, fine, it will be only in the forward direction. So, we will get a transmitted beam or forward scattered beam, whatever. Then we will be having a fluorescent X-ray. Fluorescent X-ray, definitely we have discussed the fluorescent X-ray is because of the absorption, X-ray absorption. In terms due to the X-ray absorption, we will have a fluorescent X-ray, which is basically the characteristic X-ray for this one. Then we will have a scattered X-ray beam here, and we will have different type of electrons here. So, let us discuss first the electrons, then we will come to scattered X-ray. Electrons, we will have photoelectron, which is a part of this X-ray absorption process. So, true absorption, in the true X-ray absorption process, we will be getting a fluorescent X-ray and we will be getting a photoelectron, this one. Then we can have a OJ electron as well in the same process, fluorescent X-ray or photoelectron. Instead of that, we can have a OJ electron, particularly for lighter elements, the same process, the true absorption process. And we can now have in the scattering process, we can have two types of scattering. One is the unmodified or coherent scattering, that is a Thomson scattering, and we will have a modified or incoherent scattering, that is the Crompton scattering. And in the Crompton scattering, as we discussed, we are also getting a recoiling electron, the electron which basically gets the kinetic energy and knocked out of the atom. So, that is also there, and that is another kind of electron that is generated in the process. So, this basically summarizes all different processes that can happen when an X-ray beam is incident on any crystalline materials. Okay. So, out of now, if we consider only the scattered beams, we know two types of scattering, modified scattering and unmodified scattering. And only on the modified scattering part, the unmodified scattering part, coherent scattered part, Thomson scattered part, that is taking part in the diffraction, that is making the diffracted beam. So, ultimately what we can say is that diffraction is a reinforced coherent scattering. So, out of the entire scattering process, X-ray scattering process, diffraction is a special type of scattering which is happening due to the coherent coherent X-ray beam, coherently scattered X-ray beam. So, this is the relationship between the diffraction process and the scattering process in terms of the intensity of the diffracted beam. Earlier we have derived this relationship, and there we have seen that diffraction is basically a special scattering because it happens in a particular direction where the Bragg's law is satisfied. Now we are saying diffraction is a special process or a special type of scattering where we have only coherent scattering. Diffraction, all others are incoherent scattering, Crompton scattering, a part of that, only a part of that which is coherently scattered due to the Thomson effect, that will form finally the diffracted beam in terms of intensity. Okay, fine. So, from there now we will be considering the scattering by an unit cell. Okay. So, what is this? Now, the expression for the intensity of a diffracted beam considering the coherent scattering, it only considered coherent scattering now, and we will not be considering any incoherent scattering, the first thing. So, what we will be considering now is this coherent scattering not from one single atom, but from all the atoms which makes up a crystal. So, we have to now add it up. Earlier we have, and we will come to this, earlier we have seen how the electrons, how we are adding up the waves coming out of individual electrons in order to find the final diffracted beam from an atom. Now, we will consider individual atoms, the diffracted beams coming out of individual atoms, how it will make the final diffracted beam from a complete crystal. Okay. So, and this also we have seen that the atoms are arranged in a periodic manner in the space, and that is why the scattered radiation, finally the scattered radiation is limited in certain definite direction. So, we have seen that even the Bragg's law is satisfied, we were not getting intensity due to the crystal structure, due to the atomic arrangement. We have seen this base center, the difference between base centered and body centered orthonomic cell. In one case from 001 plane, one case base centered case, we were getting an intensity, and in body centered case 001 intensity was not there, just simply because of the atomic arrangement. So, that's why when we calculate, when we consider the atomic arrangement, atomic positions, and we have to consider where exactly these atoms are located, that also is important when we consider or when we try to calculate the intensity of the X-ray diffracted or intensity of the diffracted beam coming out of this entire unit cell. Okay. So, the goal here, when we calculate this scattering by an unit cell, the goal here is to find out the intensity of the beam diffracted by a crystal as a function of its atomic position. So, the final expression will contain the diffracted beam intensity with respect to the atomic position. If we can derive such an expression, then that will help us to understand what will be the diffraction or what will be the intensity of the diffracted beam from any unit cell in terms of the atomic position. That is what we will try to derive here. And as I already said that this, to calculate this, that final diffracted beam coming out of an unit cell, this is basically what we have to consider here is the phase difference that happens between these different atoms which are located at different positions. Okay. And this problem is very much similar to the way we have calculated the final, we have find out the final diffracted intensity from an individual atom. Here also what we did is that we have calculated, we have taken or we have considered the waves coming out from different electrons, and then we have considered the phase difference between these waves between different electrons, and then we try to derive an expression for any arbitrary directions. We have seen that in the forward direction the intensity is highest because in that direction all the waves are in phase, and if we move on from any other direction the intensity will decrease because the phase difference, now there will be a partial interference because the phases are different from this. So, here also we can do the same thing, the waves we are instead of this electrons we will be considering the atoms, and what we will do is that the waves that is scattered by individual atoms here in a unit cell, these atoms will have, of course, will have certain phase difference between them due to the different atomic position, the position. For example, if you consider this body center orthonomic cell, the atomic position of this corner atoms and the atomic position of this body center atom, this position is not exactly the same. So, that is why the atoms, if we consider the X-ray beam that is coming out of this corner atoms and the X-ray that is coming out of this position, this atom, they will be at different phases if we measure in some direction, some individual arbitrary direction. If we try to see that or certain direction which is Bragg's defined direction, if we consider that Bragg's law is satisfied for certain direction, if we try to capture the diffraction or try to calculate the intensity of the diffracted beam, we will see that the atoms or the waves coming out from this corner atoms and the wave coming out from the base centered body centered atom, they will have a different phase, maybe around that. And we have to basically finally we have to calculate, in order to calculate the intensity of the diffracted beam in terms of the atomic position, we have to determine the phase difference. Basically, how this phase difference depends on the arrangement of the atoms. So, if we do that, if we are able to do that, then we can find out an expression in terms of basically in terms of atomic position, how the final intensity of the diffracted beam will vary. Basically, as you understand, each of these waves, you can consider them to have an amplitude and the phase. So, amplitude of these waves coming out, if they are consisting of same type of atoms, the amplitude will be the same for all of them, but they will be differing in phase. If they are different type of atoms, that is a different situation. We will come to that when we calculate the diffracted intensity. First, we will try to calculate a general expression, and then we will see the special kind of expressions there where different type of atoms. So, their amplitude will also differ and so on. But basically, what we will be trying to calculate now is the phase difference between the atom, between the waves coming out from this atom and the wave coming out of this some other atomic position. And also we know that this entire crystalline material is basically composed of this unit cell. That is what we discussed in the last class or last to last class, that the entire unit cell or the entire crystal is composed of this unit cells. So, if we can calculate or if we can find out an expression for one single unit cell, that will be enough for the entire crystal. Okay. So, the atomic arrangement, basically unit cells are represented by the atomic arrangement. The atomic arrangement of atoms, whatever is there in one unit cell, it just get repeated for next all other unit cells. So, finally, if we can derive one such expression for one unit cell, because of the symmetry itself, that will be repeated for the entire crystal in the bulk. So, that is what we need to do. Okay. Now, the point is how we can approach this problem. Basically, the problem, best way of approaching the problem is by finding out the phase difference between waves scattered by certain electron. So, in this schematic, you can imagine that I have an electron or I have an atom, sorry, I have an atom in the position A, which is the origin basically, and then I put another set of atom or this atomic plane, whatever we consider. We consider that along through this origin, there is an atomic plane that is going, and like that I have continuous planes. I have one set of plane here, one set of planes here. These are, we can express them some arbitrary H00 type of plane. And then with respect to this plane, if I put another atom, which is again arbitrarily put a atom somewhere, then the X-ray beam which is coming scattered by this atom and X-ray beam scattered by this atom, what is the phase relationship between them, what is the phase difference between them, and then I can take a summation of them, I can find out an expression and I can sum them up along certain direction, which is again related to the Bragg's condition. I can find out at certain direction, I can find out an expression related to one set fixed atom in origin and one arbitrary atom anywhere in the in this two-dimensional space. That is what we are considering. We will first calculate in two-dimensional space and then we will extend this in three-dimensional. Three-dimensional will not extend this, we will just simply write the expression because it is much more difficult. Okay. So, that is how we are going to do this, and this basically X-ray scattered by the what we said in this atom, the X-ray beam coming out of this atom, how it is affected by any arbitrary one which is again sitting at x direction and at a distance x from this A atom. That is what we have to consider, and if we write this, then we can find out something of this sort, an expression with which we will just start, sorry, we will start with here and we will possibly continue this in the next class. Okay. So, what we can write is basically like this, that we take this atom A here, this one, and this another atom we take atomic plane here, somewhere here. As you understand, both of them are from this H00 family of planes. So, from the Bragg's law, from this geometric consideration, you know already, we can write the path difference between them. Let us say, imagine that Bragg's condition is satisfied for them. We can write down the path difference between them, that is this delta 2 bar 1 bar, okay, delta 2 bar, okay, sorry, I think, okay, delta 1 bar 2 bar. This we can write from this geometric consideration, we can write as MCN. So, basically this construction, we are now considering this construction MCN. This is the path difference between the rays 1 bar here, this one, and 2 bar. This is basically just the way we prove the X-ray Bragg's law here. So, this we can write it as this 2D, and since this is from A00 plane, and sin theta theta is basically this angle, incident angle, and this should be an integral multiple of lambda, because Bragg's law is satisfying. That is what I imagine, that Bragg's law is satisfying for this A00 type of plane. So, this kind of an expression I can very safely write here, and also I can see that this D, that is the distance between these atomic planes or interplanar spacing, this D H00, this from this construction I can write it as AC, which is again A by H. So, A is the complete, this if we imagine that A is some lattice parameter or some lattice parameter, then this is the that is what I can write as A in terms of lattice parameter, and H is basically the distance between this A to C. So finally that's what I can write for interplanar spacing in terms of something like lattice parameter and the final intercept that it makes on this lattice parameter. Okay. So, now we are calculating for an arbitrary this plane, we already placed an atom here, which is again arbitrarily placed at a distance x from this A origin, this atom x from here, and if we imagine, if we consider this ray 3 bar ray, this one here in this direction, if we consider the same direction where the Bragg's law is satisfied, if we consider this direction, then what we can get the path difference, sorry. So, we can get the path difference between these two rays 1 dashed and 3 dashed, this rays. So, the path difference between this one and path difference between this one, this will come out to be from the same kind of consideration, this come out to be this RBS. Okay. So, this RBS is basically RBS, this one. Okay. From this construction again we can use it, the same geometric consideration, and what we can find out is basically the path difference is AB into AC by lambda, and AB is basically this distance which is x, and AC already we have seen AC is something like this, and this is the lambda value here. This is coming out to be same from the same construction, same way we are considering the path difference between, or the phase difference here. This is the phase difference in terms of the path difference. We have finally find out the phase difference in terms of path difference, and same way now we are finding out the phase difference between these two waves in terms of the path difference here. Now, the phase difference can be expressed in terms of angular in a way. So, phase difference can either be expressed in terms of path difference, or phase difference can be expressed in terms of angular difference as well. And angular difference, we know that for an angular difference, if we draw it in this way, then we know for a complete wavelength lambda, we have a phase difference of 2 pi. So, if we bring that and we put this as the phase difference in angular means, we can get this to be this value lambda by 2 pi, and if we write a specific one, that is phase difference between this 3 bar and 1 bar ray, this will come out to be this delta 3 bar 1 bar by lambda into 2 pi. So, finally, this expression will be coming out to be of this value 2 pi h x by a. We are just putting all the variables here, and if we express the fractional coordinate. So, this b value if we express in the fractional, in terms of fractional coordinate as this x by a, then finally what we can get is an expression of this sort. The phase difference between these two will be expressed as 2 pi h u. So, this is the final relation, phase difference between these two rays, one coming out from origin and one coming out from any other place, any arbitrarily placed atom, any other atomic plane. One is the atomic plane because of which for which the Bragg's condition is getting satisfied, and another one is an arbitrary plane placed, arbitrary set of atoms placed anywhere in this entire drawing. So, the phase difference between them we can find out from this expression. So, we will stop it here and we will continue in the next class. We will continue more with this phase difference, determination of phase difference for various ways. Okay, thank you.